Again, good morning, everyone. The session is being recorded, including the chat. Okay, so we are going to study simple harmonic motion using simulation, and also we are going to study Hooke's law. So these are two different, but they are actually interrelated physics concepts. Okay, there are different subchapters in physics because simple harmonic motion happens not only with a spring, okay, it also happens with different equipments. When you say simple harmonic motion, when there is a synchronous movement of objects, for example, a pendulum, the swinging of the pendulum, or even the movement of the moon around the Earth is actually a simple harmonic motion. It's a repeating motion that happens in a regular interval. So we are going to study that in a spring. We will also verify what we call Hooke's law and use it to find the spring constant K. And then we are going to use or combine these two to actually verify the value for gravity. When someone asks you the gravity, what's the acceleration? You will answer 9.8 meter per second squared. But how do you get 9.8? So today we are going to calculate the acceleration due to gravity. Okay. At the end, we will calculate what we call the elastic potential energy that is stored in a spring. If you remember the acceleration experiment that you did in the lab, where you use a spring to launch a car in the velocity and acceleration experiment. Okay, so what's causing the car to launch forward? It is the spring that we are inserting in the launcher. Okay, so how do we do this experiment? Well, this is Hooke's law, by the way, which is we are going to verify. Okay, how do we do the experiment? Let's go to our uh, this one here. Okay, now in the lab, this experiment is actually computerized. The computer will graph what we call the movement or the oscillation of the spring, and we will just count the time for 10 vibrations. So we just automate it to make it easy. Here, okay, it is almost computerized as well, except that when we gather the data from our spring, what's going to happen is we have to count manually. Okay, so basically what's going to happen here, we are going to hang a mass on our spring. Okay, you can adjust the spring length, strength. The spring strength basically is the K, the spring constant. Okay, but here the value is not given, so I will suggest to make it small here at the top, because if you have the spring strength small, the vibration is much more slower. Okay, because if the vibration is faster, it's more difficult to count the number of vibrations accurately. Okay, so if we look at the table, we have to add load, that's masses, to our spring. Okay, this causes the spring to extend. So let me just, oh wait, I lost my sharing. Okay, so we are going to add masses, and then we are going to make the spring vibrate. From there, we will count the time for 10 vibrations, and then the time period. The time period is the time for one vibration, okay? And then square this time period. So this one is 10 vibrations, time over 10, to find t here. By demonstrating it, it will be easier for you to understand. Okay, so first, I suggest that you start at the lowest mass available, which is 50. Okay, you can stop the vibration by clicking this button here. Okay, from the we call the resting position. Okay, this one, this line, by clicking this or putting a check on the resting position, this is the neutral position. That's the position of the spring when you don't pull it down. Okay, so what you want to do is to actually pull down the spring and set it to vibrate. Okay, and then we are going to use a stopwatch to take the time for 10 vibrations. So when you count the time for 10 vibrations, I will make the vibrations slow. Okay, there. You see at the bottom here, I will make the vibrations slow. Right over here. Why? Because I want to show you how to count the vibrations. Okay, so again, I will stop the vibration. I will pull the spring down. When you pull the spring down, each time that you add masses, okay, for example, from 50 you change it to 60, you have to pull the spring exactly the same amount. Okay, exactly the same amount. If you want, you can also, instead of pulling the spring down, you can also push it up like this. Okay, if you want, you can go maximum like this. But that, of course, will increase the vibration, so it will take the time, it will take a longer time to measure the vibrations. Okay, so I will suggest lift the mass up to the line like this and let it go. That will allow you to make the extension of the spring constant, even if you change the masses. Okay, so let's start with, let's stop this one. Let's start with 50 grams. Okay, 50 grams. So in your data sheet, you will write 50 grams. Let's make it by 10 grams, for example, 60, 70, 80, 90 grams. To change gram to kilogram, how do we calculate it? Anyone? Will anyone give me the answer? From gram to kilogram, how do you calculate it?
Divide
We
by
divide by 1000.
1000.
Okay, excellent. Divide by 1000. There's a technique. You don't actually have to use your calculator. Okay, so the technique, when you say 50, the decimal is here, right? And when you say 1000, how many zeros are there? 3. So just move the point 3 times to the left. 1, 2. Now there's no more number, so add 1 0, 3. So when you move the decimal 3 times to the left, you are actually dividing by 1000. Now, if you want to check, of course, you can take 50 divided by 1000 in your calculator, and you will see that it is 0.05. Okay, so it's easy, right? So 0.05, 0.06, 0.07, 0.08, and 0.09. So that's how you can divide easily by 1,000, by 100, even by 1,000,000. Okay, so the load is done. Let's take the time for 10 vibrations. Okay, so let's go to our simulation. Which one is it? This one. Okay, lift until the mass is at the line and release. So how do you count 10 vibrations? Okay, when the object reaches the original position, that's 1. Okay, and then it will go up again, that's 2, and then that's 3. So that's how you will count the number of vibrations. Okay, now let's do it in the normal speed. Okay, lift, and then you see how fast it will go. So you have to count carefully. From the top, the mass will go down with the maximum extension of the spring and go back up to the line. That's 1 vibration, 1 cycle. We start the timer at the start of the cycle. Okay, so in this case, I will suggest if you have an iPhone with you or an Android phone or a stopwatch with you, you can take the time outside of the simulation. Okay, but if you don't have, you can use this timer here. Okay, so I will start from the top. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you must stop the stopwatch at 10. Okay? In order to verify if your answer is correct or your timing is correct, you can repeat it. So let's say 8.2. Okay? So initially, let's write it here. Time for 10 vibrations, 8.2. Let's go back to our simulation. Okay, I will reset it. Reset. I'll place the object at the line or the mass. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 8.02 and 8.20, I think it's fairly accurate, okay? So that's what you will do. If it's hard for you to take the timing, you can make it slow vibration here, okay? But don't fall asleep by taking the timing. So once you have done 50 gram, go to 60 gram using the adjustment at the top, okay? So now that's 60, lift it up to the line, okay? You can start slow, by the way, and then go to normal, okay? So from the top, click start button for your timer, and then wait for the first cycle. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 8.96. Go to the table number 1 and record the time. 8.96. It's actually easy once you get the hang of it. Okay. Um, Once you have the time for 10 vibrations, you have to complete this table. Okay. Now it's time to take the time period. So for the time period, you will just take this number here, divide it by 10. Okay, this number divided by 10. So 8.2, if you divide it by 10, you get 0.82. This is 0.896. So let's write 896, 820, 896. Okay, again, you have to complete this table. Next, you have to square this number. Okay, so you have to square it. You have to square it. So if you want to square it, let's use our calculator in the computer. Okay, 0.82. So you type 0.82 squared. Okay, you get, not sure if that 0.82. Let me verify with my calculator. Yes, 6724. So you write it here, 0.6724. 6724. There you go. Okay. So here 0.896 square, 0.896 square, 8028. So 0.8028. Again, you have to complete the table. Okay. Any questions, Shabab, how to make table 1? Any questions how to make table 1?
Yes, Doctor.
Hello?
Again, the time.
Can you speak louder, please?
I said again in the time.
Ah,
Time
how to
being.
get the time? How to get
Yes.
the time? Okay, sure, sure. Let me show you how to get the time again. Okay. So going back to the
No,
simulation
Doctor,
here,
Doctor. Here. I know this, but in the
you know this.
yes,
Okay. You
the
how to
second time.
get the time period. You're
Yes.
talking about the time period?
Yes.
Okay. This is the time and this is the time period. That's important. Okay. So to get the time period, we will repeat it.
How?
You will simply take this number
Yes.
and divide it by 10. So 8.20 over 10. Clear?
Yes, clear.
Okay. So
Another.
you will take the other one. Well, the same thing. Divide by 10. And if you have the answer here, divide by 10. If you have the record here, divide by 10. Kullu divide by 10.
No. T2, Doctor.
This one. You said another. So you square it.
But
So this
it's
one is 0.820. Okay, you take this number and you square it, becomes that number. Okay? Is it clear now?
yes.
Okay. So once you finish table 1, again, uh, let me write the value here, just to write it. Okay. So 0.820, 0.896. Once you finish table 1, you have to make a graph, okay? So if you go to the calculation, this is from table 1. You have to read the notes carefully, okay? Graph number 1 from table number 1 is a graph of t squared versus m. So when you say t squared versus m, take note of this. This is true all the time, okay? The first value that's mentioned is always the y-axis, and the second value is always the x-axis, okay? The first one y, the second is x-axis. That means y-axis is t squared, and x-axis is mass, okay? Y-axis is t squared and x-axis is mass. You have to graph the value, okay? In the x-axis, you start with the masses. This is 50, 60, 70, 80, 90, okay? Your graph starts from 0, okay? Your graph starts from 0, so you can divide it by 10, for example. 10, 20, until you reach 100. And then in t squared, look at the values. So 0.67, 0.8. So you can make the graph, for example, by 2's, okay? By 0.2. Next line will be 0.4, 0.8, 0.6, 0.8, until you complete the line, okay? What's going to happen? You will get a straight line, or approximately a straight line. You have to find the slope of that line and write it here. So how do you find the slope of that line? The slope equation is always the same. It's equal to y2 minus y1 over x2 minus x1. So that means 2 points from your line. Okay, 2 points from your line. Let's say this point. I cannot write on the point now. Let's say this point here and this point here. What's the value of x and y? What's the value of x and y? You substitute it here. So this is point number 2 and this is point number 1. Okay, that's how you get the slope from the graph using your pencil and your pen. If you want to graph it in Microsoft Excel, you can. Okay, so if we open Microsoft Excel, let me just open it. If you open Microsoft Excel, what you can do is you can enter the data of your X and Y axis. Okay, so let's go to our X and Y axis. So let's say the data says that you have to graph t squared, okay, t raised to power of 2, and you have to graph t squared versus m. So what do? You take the masses first. Let me just arrange this one. Okay, take the masses. Because that's the x-axis, you have to place it on the left. The y-axis, you have to place
Teacher,
it on the right. Mhm.
the result of graph, it's always a straight line or what?
It is ideally a straight line, okay? But sometimes you make a mistake in one reading, so this one will not cause a straight line. But ideally, perfectly, you want it to be a straight line, okay?
Okay,
So
okay.
again, make the graph. 1 second. So you make the graph in Microsoft Excel. Will make it easy for you, okay? So in the masses, you write the masses there. You can start with 50. 60, 70, 80, 90, or 100, if you have 100, for example. Okay, and then t squared is this value here. At 50, what is the t squared? Okay, 0.0.6724. At 60, 0.8028, and so on. Once you have the complete data, you select it. Okay, you select the data like this. Without the x and y, you can keep m and t squared there. Okay, select the data like this, and then go to Insert, Scatter. I showed you how to make the graph in Excel in the other experiment, Joule's equivalent of heat. So the technique is the same. Okay, the technique is the same. Now here in the graph, you can actually insert, for example, if the mass is 0, what is t squared? Is it 0? Okay, you can actually insert it to make the graph start from 0. However, um, there is one source of error that we are not considering here. Okay, what is that source of error? The mass of the spring is not included because the spring itself, if you go to the lab, this device, the spring, the coil, the mass itself is not included. Okay, but anyhow, since it's only simulation, so it's fine. You will see that this is a straight line. Click on the point and right click, add trend line, and you will see that it's actually a straight line. Okay, and from the trend line options, click display equation on the chart here. Okay, and it gives you, again, as I explained last time, it gives you what we call the the y-intercept form of the slope. Okay, so for my students, I ask my students to make the graph like this. They will make a screenshot of their graph using the snipping tool like this. Okay, and then from there they will write their name, for example, Tim, section ID number 12345 6, and section number 1, something like this. Okay, where is the slope in this equation? The y-intercept form of the slope is y is equal to mx plus b, where m is the slope, the number before x. Okay, so this is x. Where is the slope? Let me highlight the slope for you. The slope is this number here, 0.0134. Go to your data sheet, okay, and write the slope, 0.0134. Let's go page down. The slope is 0.0134. Just to check it, 0.0134. Okay. So once you have the slope, calculate the k. Okay. So k is equal to 4 pi squared over the slope, 0.0134. Take note, Shabab, that each of you, there is possible that your slopes will be the same, okay? Because the slope, which is used to calculate k, will change if you go to your simulation and adjust the spring strength here, okay? So if you don't want anyone copying your data, don't just go to the small. You can make adjustment in the spring here. You can go up to the large spring, okay? But take note, if you use the large spring, the vibration is fast. So you can slow it down, okay? So that you can take the timing properly. So that's how you will accomplish table number 1 with calculation number 1. Any questions? Any part of this setup that you want to clarify? Go ahead and ask me now. No questions? Silence means no questions.
In the graph, you
Yes,
need
Basil.
we need time square and mass. Mass in which unit? Gram or
Mass and t squared. Okay.
yeah.
Oh, you are right. You are actually right. Um, okay. I forgot about that one. That was a very good question. Okay. Actually, the mass has to be the kilogram value, not the gram value, because we are going to calculate gravity. If you remember the objective, let me go back to the objective. We are going to calculate acceleration due to gravity. Okay? And when we calculate acceleration due to gravity, we have to use at the end the value of the mass in kilogram. So that's the good thing about Microsoft Excel because you can change the value. So 0.05, 0.06. Okay? As you can see, this is the advantage of using Microsoft Excel. So if you change the values, look what happens to the slope, okay? So let's select our point again and then add trend line. The trend line is already there, display equation on the chart, okay? And what's gonna be the change? the unit of or the number of the slope is the same, only the decimal will change there. It becomes 13.40. Okay, so let's go back to our calculation. Where is it? Here. Okay, so change this one. It becomes 13.40. So our slope is 13.40. That's a very good question. Okay. Any other questions? Shabab, no more questions? If there's no more questions, we will go to table 2. If there's no more questions, we're going to table 2. That's it? No questions?
Yeah, Dr. Gafar.
Okay. Okay, we're going to table 2. In table 2, this is um, Hooke's law. Okay, so table number 1 is simple harmonic motion. Table number 2 is Hooke's law. Now, remember in Hooke's law, it is usually used to find the value of k, the supreme constant. However, we find the value of k using simple harmonic motion. Okay, using a different equation for simple harmonic motion. So in table number 2, we will use the value of k to actually find the value of gravity. Okay, so how are we going to do it? First, we are going to use the masses again. Okay, so we will type the masses here, or we will write it here. We can start with by hundreds if you want, but I suggest we start by 50. Okay, so let's put here 50. You can put any mass that you like. Okay, so let's say 50, and then 70, and then 90, and then 110. Okay, because the masses can be adjusted. If you go back to the simulation, you can choose your own masses here. Okay, up to 300 grams. So let's go to back to our data sheet. One thing that you should not change when you're choosing the masses, it's okay. But one thing you should not change in the simulation is the strength of the spring. Between table 1 and table 2, the strength of the spring must remain the same. It must be exactly the same. So in table 1, if you use a small, table 2, you have to use a small also. Okay? Do not change this part here. So let's say I will take 50, and then I will increase by 50 also. So in my data sheet, 0, than 50. Increase by 50 means 100, 150, and then 200 grams. Okay? In kilograms, again, divide by 1,000, so 0.05, 0.10, 0.15, and 0.20. Okay, you will measure only the extension without the simple harmonic motion, without the vibration. Okay, so go back to our simulation. You can remove the clock now because you're not gonna do the vibration, but you will need the ruler or the scale. Okay, now this scale is in centi. So when you don't have a mass, remove the mass, you can just pull it out and drop it. Okay, when you don't have a mass, 0, the extension of the spring is also 0. Okay, so in the simulation, this is how you should arrange it. The 0 of the scale must be with the spring. So use the edge of the spring on the right here to indicate 0. This point here. Okay, let's make a movable line. This point here with the laser, okay, that's your 0. So take the scale and place it here. Okay, now you can remove the movable line, just move it up like this, and then hang 50 gram on your spring. Once you hang 50 gram on your spring, you have to wait for it to stop. Okay, or you can just stop it. If you stop it, that's the position. So take note, where is the scale? Okay, it's a little bit hard to see, and you cannot zoom in. I tried zooming in, okay, but it's not zooming in here. But what you can do, Shawab, actually Blackboard, you can make zooming, right? So do you have to open the Blackboard to zoom it? No. Actually, I can zoom it for you just to read. Okay, just to read. Okay, you can actually move the pointer so that you can read exactly. Okay, so what's the reading here? This is 10 centi, 11, 12, this is 15, this is 16 centi. So I can see it clearly, 16 centi, because I'm zoomed in. I will take my screenshot, okay, and show you the reading. Okay, this is zoomed in. Okay, this is now zoomed in. So, 1 second. Okay, so while I'm zoomed in, I can read the extension of the spring. Okay, so the extension of the spring, this is 10 centi, this is 15 centi, one line after 15 centi, this is 16 centi. Okay, this is 20 centi, so 16, 17, 18, 19, 20. So take the value 16 centimeters and record it in your data sheet. Okay, remember that the scale, this mastera is in centimeters there. Okay, so the scale is in centimeters. So let me just bring it back there. So go to your data sheet at 50 grams, 16 centimeters. It has to be in meter. That means divide by how much?
0.16.
Okay, divide by 100. This is equal to 0.16. You don't have to show the calculation in your data sheet because it's just a table. So just write the value 0.16 meters. Okay? Again, why do we have to change it to meter? In order to get the value for gravity, because the unit of gravity is meter per second squared, not centimeter per second squared. Okay? So let's go back to our simulation and take one more reading. Okay? What's the next value for our mass? We increase by 50. So let's make it 100. Okay, now it's 100. You can see the number is at the top. Stop the vibration and then pull down the laser pointer like this. Take your snipping tool. Shabab, this tool is very useful for me. Okay, take the snipping tool and you can zoom. Okay, in your snipping tool. So, well, not this one exactly, but if you go to Paint, for example, so take a screenshot here. Go to Paint because everyone has Microsoft Paint. I don't know if you're using Apple, if there is any equivalent. So in Paint, you can actually zoom in. Okay. So in Microsoft Paint, you can zoom in and then you can read at this point, this is 30, 31, 32. Okay. So you know that this is 32 centimeters. I'm closing it now because I'm not going to make another reading. Okay. So just write it here. 32, 0.32. Yes, Ibrahim, you have a question? Ibrahim?
Yes, doctor. Where
Go ahead.
we bought the skill?
Where did I take the scale?
Where we bought the skill? On which line? On which place?
Again, please make your question clear. Hada Mastara? Hadi?
A. Yes.
Where did I take it? I take it from here. Okay. I will start from the beginning. Remove the mass. That means zero mass. Take the scale and put
Yes.
the edge, the zero. Okay. Put the zero at the edge of the spring like this.
Yes.
Okay. That's the starting position. But then at 50 gram, for example, hang, stop the vibration, and take the reading. And then change the mass to 100 gram. For me, okay, you can change it by 20, by 10, by 15 if you like. And then take the reading. Change the mass to 150 because I want to use by 50. Okay. Take the reading. As simple as that. Okay.
Okay, clear.
Okay, good. So once you have completed the data here, you have to complete the data. Okay? Take note of the XM, the maximum extension at the highest mass that you're adding. Why? Because at the end, there's a calculation for the energy stored in the stretched spring. That's a potential energy. Okay? You will use the calculation 1/2 is equal to kxm squared. So the xm here is the maximum extension here in this table. Okay, it's the maximum extension xm in this table. Take note of that one because you will need that later. Okay, what to do with table number 2? You will make a graph again. So you will make a graph of extension versus mass. This is the graph. Okay, so just to show you how it should look like. Again, mass is on the x-axis, extension is on the y-axis. Again, your graph has to be a straight line. Ideally, it has to be a straight line, okay? Find the slope of the graph, write the slope here, and then if you take the value of k from table 1 and the slope from table 2, that's slope number 2, okay? You multiply them together, you will get the value of g, gravity. So let's say, for example, the value of g is going to be, let's say only by calculation, okay? You get the value of g and you get, for example, only 9.6, okay? For example, so show the calculation here and then you get the value of g, 9.6 meter per second squared. What do? You take that value and substitute it in this equation to get the percentage error. Okay, so the real value, 9.8 minus 9.6 over 9.8, multiply, don't forget multiply by 100%, and that gives you the percentage error here. That's how you will calculate gravity and check your percentage error with the real value, which is 9.8. That's it, done. Of course, you have to calculate the energy potential in a spring that is stretched. Any questions, Shabab? Can you make graph number 2 in Microsoft Excel? Yes, you can do the same technique. The technique is exactly the same. Shabab, questions?
Yes, doctor. Slope 2. How we can get it?
Slope number 2? Same
Yes.
thing. You have to graph table number 2. This is y-axis and this is x-axis. Once you graph it, the equation for the slope is the same as this equation. Table 1 and table 2, the same equation for slope. If you graph by pen or pencil, y2 minus y1 over x2 minus x1. If you graph by Microsoft Excel, okay, you put the value of mass in the x-axis, the value of extension in the y-axis, go and make your trend line, and then from the trend line you get this equation. It's the same process, okay, exactly the same process. Any other questions? If you missed the process how to get this value, okay, I will repeat it. Okay, how to get the slope from Microsoft Excel. First, put the value of the x-axis on the left side, the value of the y-axis on the right side. But then you select the data. Okay, you have to select complete like this. But because I didn't take all the reading, it's not necessary to take all the reading for me. Okay, you can just select this and then make insert, scatter, select the points, and these are your points without the linear fit. If you remember linear fit, it's the same as trend line. So click on the points, right click, add trend line, display equation on chart. Okay, let me increase the size of the text for the equation. Once you have the equation on the chart, this equation is actually giving you the slope. Where is the slope here? The number with the x. Okay. Any questions? Now, since it's all done, I'm going to stop the recording to keep it short.